I will begin with a word of prayer. Dear Father, we thank you for this day. We thank you for the break, and I just pray that you bless this class today, Lord, and just help these students as they're preparing for the test Thursday, that you just help them to just leave no stone unturned and just to be ready, Lord. In your name I pray. Amen. All right, so we start with the new material. I'll try to leave some time at the end for your questions. So we have, up to this point in the course, talked about how to solve problems that are, well, relatively benign, constant coefficient problems. Now that's not entirely true. In the first order case, we have solved all manner of weird stuff in the first order case. Like the first order case, the things we can do for first order differential equations are really special. And that doesn't really happen again for higher order problems. But there is a general technique which is, so series and singular points is the main orders of business today. But I'm actually going to start with something that's a little bit more familiar, which is the so-called, but to begin, this is in some sense a weird starting point, the Cauchy Euler problem. Cauchy Euler problem. Now the Cauchy Euler problem is also known as the equidimensional problem. And so here's the problem. Solve, let's say, x to the n, d to the n, plus an minus 1, x to the n minus 1, d to the n minus 1, plus plus a2 x squared, d squared, plus a1 xd plus a naught, this differential operator acting on y equal to 0. Now, okay, I don't have to put the 0 there. Technically, I could put f here, right? But we're going to focus on f identically 0, which is the homogeneous case. We're going to talk about how to solve the homogeneous case. Well, the thing is, this is still an nth order linear ODE. Nth order linear ordinary differential equation. And so that means that the theory we discussed applies here. All right? So what I know then is that there exists a fundamental solution set, all right? And that fundamental solution set can be used to build a general solution. I'm going to be looking for n linearly independent solutions. And then if I was to work on the non-homogeneous problem, we could use variation parameters actually to solve that, all right? So that's why I'm always on the fence about whether or not I should include this problem on test 1. But I chose not to simplify your life a little bit, all right? Also because this is a nice example because it actually has a singular point, all right? The domain of this differential equation is not all x, all right? We have to either focus on x positive or x negative. Otherwise, the leading coefficient, I mean, if x is equal to 0, is this an nth order problem? I mean, if x is equal to 0, the nth derivative is kind of gone, isn't it? So this in some sense ceases being an nth order problem when we're at x equal to 0. To be more careful, x equal to 0 is an example of what's called a singular point for this problem. All right? The problems we've worked up to now and that are on your test, I don't think really have singular points, at least for the constant coefficient problem. Admittedly, in the first order differential equations case, those problems can have limited domains, places where you have division by 0, all kinds of funny stuff happens there. The reason this is called the equidimensional problem is if you do a dimensional analysis, what's d? D is like d dx, right? So what kind of units does the derivative carry? Like reciprocal to length units, right? On the other hand, what kind of units does x to the n carry? Well, units to the nth power, right? So if you look at every term here, we've got a balancing between units to the nth power or the kth power and 1 over units to the kth power as you look at this operator. So it's an equidimensional operator. That's why this is called the equidimensional problem. Cauchy Euler, of course, because Cauchy and Euler did everything. But the question is, how do you solve this thing? All right? And there are various approaches. Let me show you so here's the easy way. Maybe easy is the wrong term, but maybe less clever way. Usually I would say that the clever way is the easy way. Here, in some sense, I'd say that the easy way is not the most clever way, but it's a way. And that's just to guess that y equals to x to the r solves this. And I need to give this thing a name. Let's say L of y equals to 0. So I'm going to call the differential operator, which defines the differential equation, L, for lack of a better idea, L. And so if you plug in x to the r into this, what happens? What's the kth derivative acting on x to the r? What's that give us? This is d to the k minus 1 times d acting on x to the r. So what's the derivative of x to the r? R x to the r minus 1, am I right? And then we differentiate again. And that gives us r times r minus 1, x to the r minus 2. And this continues, right? Until we've done our k derivatives. What happens? We get k factors in front, right? We get r times r minus 1, r minus k plus 1, I think. Because I start out at 0, I go all the way to, I could rewrite this minus k minus 1 if you like, just to make the pattern more clear. X to the r minus k. What happens when I multiply x to the k times d to the power, the kth derivative acting on x to the r? What do we get? We get r times r minus 1, r minus k, again, is plus 1 actually if you distribute the parenthesis. And then we've got x to the k times x to the r minus k, which is just what? Right. X to the r. And which k does this calculation work for? K equals to what? If you look at it, it's going to make sense whether k is equal to 1 or 2 or 3 or 4 or whatever. So this this calculus works as we plug in and do it on each term here. So what I'm trying to say is, if we actually follow through this calculation and just straight up plug in x to the r into our differential operator L and set that equal to 0, what that's going to give us on the nth term, it gives us r times r minus 1 times r, how many? R minus n plus 1, yeah? Plus a n, r times r minus 1 r minus n plus 2 plus plus r times r minus 1 a2, I think. Yeah. Plus, oh man, poor planning on my part. R times a1 plus a naught, right? Every single term, after you multiply by the x to the k, you're left with a residual, one of these guys. Right? So if you look at it, you can factor those out, and you've got x to the r equals to 0. So apparently, we seek r such that what? R times r minus 1, r minus n plus 1 plus an r times r minus 1 dot r minus n plus 2 plus da 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 plus a2 r times r minus 1 plus a1r plus a naught equals to 0. Because if this is going to be a solution which works, then by golly, we had better solve this differential equation, because we cannot hope that x to the r is always 0, right? X to the r is usually non-zero. So if that equation that I wrote up there is going to work, if our solution is actually going to be a solution, we need that this so-called characteristic equation is met for r. It's solved. So r has to be a solution to our characteristic equation, which for this problem is this. Kind of a drag, right? What's the characteristic equation been? What, you know, if I have the corresponding problem, right, versus what? We had what? D to the n plus an minus 1, d to the n minus 1, right? a2d squared plus a1d plus a naught. That acting on y equals, that's the constant coefficient problem, right? And the same calculation done there for what guess? We would guess what? Y equals to e to the lambda x is my usual guess. And remember, we tried that guess. We plug it in. What's the characteristic? What was that calculation get you? Get you lambda to the n plus an minus 1 lambda to the n minus 1 plus a2 lambda squared plus a1 lambda plus a naught equals to 0. So you can contrast the characteristic equation for the constant coefficient problem to the characteristic equation for the equal dimensional problem, and you can see why I start with the green one, because it's much easier to think about, right? The process of creating the characteristic equation for the Cauchy Euler problem actually involves a little bit of kind of non-obvious thinking, right? You ought to be able to, at this point, just write down the characteristic equation for the constant coefficient problem without a lot of thinking, right? Right? Well, anyway. Should be some amount of, this is easy, come on. I mean, okay, actually solving that when numbers are involved could be a pain, right? But let's take a step back here. What's the characteristic equation in R, though? I mean, let's take a look at it. What kind of equation are we looking at? How many, what order equation is this? Is it polynomial, right? This is what? Nth order polynomial equation in R. Therefore, what? There are n factors here. That makes it r to the n is the leading term. So it's nth order polynomial equation in R. We know by the fundamental theorem of algebra then that there are n possibly complex solutions, possibly repeated, but there exist n solutions to this, right? Therefore, there exist n solutions in the complex number systems, right? I mean, possibly repeated, but that's fine. Possibly complex. So then the question is, what do we mean by x to the r when r is complex, right? So we face that issue again. It's just now instead of having e to a complex value, we've got the power function with a complex exponent. What's that, right? We have to address that question here to understand the full weight of our guess, all right? So let's, now, all right, so I did this derivation for nth order problems, but by and large, I tend to ask order n equals to 2 for Cauchy Euler as we go on. So let's look at some examples. So suppose we're going to solve, let's just start out relatively simple. Let's try to solve x squared d squared y equals to 0, right? AKA x squared y prime prime equals to 0. So if I follow my general derivation, I should write down the characteristic equation in R, right? we guess y equals x to the r. That implies that r times r minus 1 equals to 0. Because that's... Somebody want an umbrella? No? You're like, it's not umbrella, it's umbrella. Let's not get started on that. All right. I hope you can solve this. R equals to 0 and R equals to 1. Hooray. We have what? We have found ourselves a distinct real case. So this suggests that y equals to x to the 0, y1 equals to x to 0, and y2 equals x to the power 1 are solutions, right? My fundamental solutions, and my general solution will be C1 plus C2 x. Hooray! Now, I bet you could have probably derived that for positive x or for negative x, right? Without this middle board of complicated jibber jabber. Because what could you have done? I mean, I see it. You see it? I would just take this, divide by x squared, right? This is for x not equal to 0, right? And then this, you just integrate 2 times, right? So in this particular case, there's a way around my guessing. We could just integrate 2 times. But this comes with strings attached, right? That's only the solution for x positive, right? Or for x negative. Yeah? Even though the boxed solution gives the appearance of it existing for all x in the reals, that's not the case. This is not a solution to the given differential equation at x equal to 0, because x equal to 0 is technically outside the domain of definition for this differential equation. All right, just some. All right, let's see here. Number 2, let's see if we can make this. How could I make this complex? What would I do? X squared, d squared. I want to, let's say maybe plus x xd plus, I don't know, 9. Think like that. That should work for me. All right, in the prime notation, this is the differential equation x squared y prime prime plus xy prime plus 9y equals to 0. So what's my characteristic equation? We have r times r minus 1 plus r from that plus 9 equals to 0. Now, I added the middle term to cross out the linear term, right? See what we got? This gives me r squared plus 9 equals to 0. So I hope you guys can solve that, right? What's the solutions? R is equal to plus or minus 3i. Like, wait a minute, nobody ever told me what x to the 3i means, right? So I think a definition is in order, yeah? So definition, x to the alpha plus I beta is equal to x to the alpha times the cosine of beta natural log of the absolute value of x plus I times the sine of beta times the natural log of the absolute value of x. Let me try to give you a little bit of backstory there. The reason this is a good definition is we can think of this instead as, we can think of this as e to the natural well, and here, this is a slight abuse, guys, but you'll forgive me. Natural log of alpha plus I beta. If you're taking complex right now, you're not taking complex right now, right? Okay, so this can't hurt you. Good. Then you could think of this as being curses. I lost my x, right? X to the alpha plus I beta, but then if you believe in laws of exponents, that should be e to the alpha plus I beta times the natural log of, and we probably should put an absolute value on x there just to make sure it makes sense here. We just let x be positive to keep things simple, okay? And so this would give me e to the alpha natural log of the absolute value of x, e to the I beta natural log of the absolute value of x. So the first term just becomes e to the natural log of x to the alpha, and the second term becomes e to the I beta log x, yeah? But what's e to the log of x to the alpha is just the absolute value of x to the alpha, and the second term becomes the cosine of beta natural log absolute value of x plus I times the sine of beta natural log the absolute value of x. But we're assuming x is positive, so I can drop the absolute value bar signs here. And that is why, and I don't want you to derive this necessarily, I'm just pointing out that my definition is based on the calculation right below, which is part of a logical and complete discussion in another course, okay? But the blue boxed equation is a working definition for us in here. That's how we calculate x to a complex power. It's just x to the real power and then a complex linear combinations of cosines and sines with appropriately weighted natural logs. So what I'm trying to get at here is x to the 3i is apparently x to the what? X to the 0, because here alpha equals to 0 and we can say beta equals to 3. Yeah? So I've got x to the 0 cosine of 3 natural log of, and let's I'm tired of it. We're going to assume x is positive, okay? So 3 natural log of x. I don't need the absolute value bars, right? If we assume x is positive. Plus I sine of 3 natural log of x. Well, surprise, surprise. This is a characteristic equation, when it has a complex value, gives us a complex solution. Again, I go back to our larger discussion of complex differential equations. If we find a complex solution for a linear differential equation like this, then the real and imaginary parts of the complex solution are separately, honest to goodness, real solutions to the problem. All right? And so from this, I extract that the real part of x to the 3i, which is cosine of 3 log x, and the imaginary part of x to the 3i, which is sine 3 log x, that these are separately real solutions to the given problem. So those taken collectively form my fundamental solution set. And if I take a real linear combination of those, that gives me the general solution. That's it. So the solution, C1 cosine 3 natural log of x plus C2 sine of 3 natural log of x. Now here, it is more in our face. It's just like, you can't miss it, right? You can't miss it that x equals to 0 is a trouble point for this differential equation. It is just manifest in the solution. Log of 0 minus infinity, our solution's formula ceases to make sense at x equals to 0, right? If you take the x in this formula and replace it with absolute value of x, that would give you the solution for negative x, right? Or you could just put minus x in place of x. Then when we put x negative, the written solution would still make sense for negative x. But we cannot include 0 in the domain of the solution, right? 0 is a singular point for these problems. Any questions about this? Do you see what would have happened if my characteristic equation had actually had the solution had not been a pure imaginary solution, but it had been like 3 plus or minus, or say 2 plus or minus 3i? What would have changed? Instead of having just cosine and sine, we'd have x squared times cosine and x squared times sine if we'd had a real part. But we didn't, so we just had pure sines and cosines. What's the third thing that we should worry about for a second order Cauchy Euler problem? So the characteristic equation, it's a quadratic equation. It can either have distinct real roots, it could have a complex root like we just saw, right? In fact, we looked at the pure imaginary case because it's most beautiful. What's the other case? Repeated root, right? So what's the deal with repeated root is the question. All right, so how do we do that? So I'm going to give you a sneaky argument based on an analogy. And actually, the thing I'm about to share with you has application really across the spectrum of solutions to differential equations. And it's the iceberg, the tip of a much larger iceberg, which is not talked about enough in the calculus sequence. And if I had more time, it's something I probably would try to invest a lot of energy in thinking about how to communicate it better to students, because I think we're failing you guys in terms of communicating this idea. And so here it is. We have already looked at y equals to e to the lambda x, right? That's a solution for the constant coefficient problem. What happens if lambda is repeated? What's the solution? Y equals to x e to the lambda x for repeated, right? For repeat. Repeated root lambda, yeah? How is this and that related? How can we get from here to here? I've showed you guys various ways of deriving the x in the repeated root solution, right? We straight integrated the thing at some point. I know about 7 or 8 different ways of looking at that question. But here's one of the more fun ones, is you can think about going from here to here by partial differentiation in the parameter of the solution. See, partial lambda of e to the lambda x is e to the lambda x, right? Partial lambda of lambda x, but what's that? Holding x fixed while varying lambda, this is just x again. So that's x e to the lambda x, which is, of course, our repeated root solution, right? So what should the repeated root solution be to the Cauchy Euler problem? We've got y equals x to the r, right? So my question is, what should we put y equals fill in the blank with r repeated? What do you think goes there? I say by formal analogy, if nothing else, we ought to be able to get from there to there by partial differentiation with respect to the parameter of our solution. So what is that? What's partial r of x to the r? Calculus 3 is a prerequisite for this course, right? Yep. So why is it not rx to the r minus 1? Because that's the derivative with respect to x. Right? So with respect to x, this is a power function. But with respect to r as a variable, x is the base, right? So x is fixed. It's more like differentiating. Analogy to this would be something like partial t of 3 to the t, right? If I'd asked you guys that, you'd be like, oh, natural log of 3, right? 3 to the t, maybe, right? So here, x is like 3. So the answer is log of x times x to the r. Because it's actually an exponential function in r. And in fact, that is the other solution in the repeated root case. It's not just a formal analogy, it actually works. You can plug that in and check it. So my third example, let's see here if I can come up with something. So I'll start out with my, let's see here, x squared d squared plus 7xd plus 9. Sure, why not? Acting on y equals to 0. I think this should do nicely for us. In other words, in the prime notation, that's x squared y prime prime plus 7xy prime plus 9y equals to 0. There's my Cauchy Euler problem. So write down the characteristic equation. In this case is r times r minus 1 plus 7r plus 9 equal to 0. You do the math. You got r squared plus 6r plus 9. I did this on purpose. That's what? R plus 3 quantity squared, right? So therefore, R1 equals to R2 equals to minus 3. Yeah? And so that gives me my first just plain Jane, although this is starting to get weird, right? X to the minus 3. So you mean reciprocal functions are possibly solutions to the Cauchy Euler problem? I mean, that's something we have not seen before as a solution to a second order problem, right? It's kind of out there. And this is so much worse. y2, x to the minus 3 natural log of x. So that's log x over x cubed. So the general solution, y equals to c1 over x cubed plus c2 natural log of x divided by x cubed. There you go. That would be the general solution. Again, I'm assuming what? I'm assuming x is greater than 0. Yeah. And that is the Cauchy Euler problem. Yeah. Aha. So if we had... No, let's see here. So in the before here, what happens if you partial lambda this again? Right, you get x squared e to the lambda x, right? So if we were to partial r this thing, if we believe in this technique, what happens? Oh, it actually brings down a natural log of x squared x to the r. Yeah. Yep. There are other ways of deriving this. You can make a change of variables that changes a given Cauchy Euler problem into a corresponding constant coefficient problem. You can write down the general solution to the constant coefficient problem and then transform back, is another way this can be done. But that transformation process is so complicated, in my view, that I don't think it's worthwhile. Yeah.
So I get why x can't be 0, but why can't it be negative?
It could be negative. So I'm assuming x is greater than 0, which means that I wrote natural log of x. If you wanted to let x be negative, so what I'm trying to say is this is the solution for positive x.
Okay.
The solution for negative x is not that hard to find. We could write that if you wanted to be greedier. But I like to think of the domain of definition as an interval. So that means either I need to take the connected set of real numbers positive or the connected set of real numbers negative, one or the other. And I try to keep it positive in here. So, you know. What? Sorry. You guys going to the game? Are you guys excited about the game? Usually, you could say that at any point in time, and usually it would pay off, right? I mean, it's the conversation you can make with people. You just ask them about the game. You don't actually have to know about the game. You just say that. And then people will respond and say, oh, yeah, the game, But sometimes, there's the danger that there's no game, and then people will catch on to your ruse. So you see how I am. Sorry. Should I try that joke in 201 and see how it goes? I don't know. Maybe.
Probably be better.
Probably would be. There's somebody in there who's going to be thinking about a game.
Right.
You guys are just thinking about like.
Wait till Friday.
Wait till Friday?
Yeah.
Is there a game?
Game on Saturday.
Why didn't you guys assume I was talking about that game? It's too far away. Oh. Oh, it's after, you only think of the differential equations test right now. I respect that answer. That's a good answer. So let's talk about series solutions and singular points. So the theorem, this theorem I'm about to write down for you is amazingly greedy. And here's the theorem. To solve, suppose we've got a2 y prime prime plus a1 y prime plus a naught y equals to g, right? Where a2, a1, a0, and g are functions, all right? We may suppose y is equal to a sum n equals 0 to infinity of a sub n times x minus x naught to the n. Oh, poor choice on my part. I already used the a's, right? So we need to come up with a different nomenclature for the coefficients in the solution. Let's say c sub n, all right? There we go. Problem averted. But if a sub n wasn't already used up for a given problem, I might call the coefficients a sub n. All right, it's not written in stone that they have to be c sub n. You could put a sub n there. You could put, I don't know, pick your favorite coefficient. Now, you can suppose your solution has that form, all right? We will find there exists choice C0, C1, C2, dot, 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 and so on and so forth, which make, let me call it star a solution to, I'm going to give this guy a name. What do you want to call it? Drake. Kind of big right now, right? Here. There you go. Solution to Drake. We solved the Drake problem. So the solution to Drake is a power series. And, moreover, star serves to solve Drake on a disk in the complex plane, which extends to the nearest singularity of, all right, so I chose, well, singularity of Drake. Now, to give some more singularity, I mean, okay, so what do we mean by that? There's different ways. To capture what I mean by a singularity of the differential equation, perhaps it's best for me to divide by A2. All right? But essentially, this is the point. If A2 was 0, that's a singularity. If A2 had a first derivative, which was 0, I think that's a singularity. Let me just, it's easier for me to write it this way. If we have y prime prime plus A1 over A2, y prime plus A0 over A2y equals to g over A2. Let's trade Drake in for a simpler, maybe this is how I should have started. I'm sorry, guys. I forget when I get away from this stuff what's the laziest way to discuss it with you guys. So maybe it's better, a better Drake. A better Drake. What would be a better Drake? Did I hear Kanye? I don't think that's an appropriate. I don't think that's an appropriate comparison. Let's see here. Different generations there, right? I mean, I don't know. By prime. It's like comparing. What would be an apt comparison? I don't know, like the Beatles to I don't know. What do you want? Air Supply? I don't know. You guys don't know what Air Supply is. That's, you know, some things are better left forgotten. Let's see here. So, oh man, now see, I'm not going to have to edit this. I've just offended my on my. Did I compare Drake or Kanye to the Beatles? Have not both of these musicians at various points in their careers equated themselves with the divine? Some subset of those musicians have, in fact, claimed, divine equivalence, let's say. Maybe not equivalence, but certainly in terms of what swagger, or what's the right word here? I don't know. I'm not a musician by training, so I don't know how to say the right kind of, what's the word? Did you say Ringo, or did you say lingo? Lingo. Okay, lingo. Let's not bring Ringo into this. Let's see here. F. Okay, so this is a better Drake, which we're debating what that should be. I don't know. Maybe Drake 10 years from now, right? I don't know. Let's see here. Have we learned nothing from McConaughey? Let's see here. All right. Okay, so this is easier for me to discuss because a singularity in this, singularity of the above, means either B1, B0, or F have a singularity. And I think the term singularity as it applies to a function is something you're already familiar with, right? Ever since Calculus 1, we've been talking about vertical asymptotes, right? That's a singularity in the function. Something like that. A place which is outside the domain of definition. Let me just throw some functions out there. You tell me they're singular points. So, for example, if I had B1 equals to 1 over x squared plus 1, what are the singular points? Yeah, let me make it simpler. How about b1 equals to 1 over x squared minus 1? That one, you guys will get better. That's 1 over what? X plus 1 times x minus 1, yeah? So that has what? Singular points x naught, let's say, equals to plus or minus 1, right? Maybe x, maybe I call them x sub star, right? Yeah, they're singular, like Drake, right? Is Drake coming to combo? No? He's got that song, God's Plan, right? Isn't that like Christian music or no? I don't know. That's what? You're like, don't encourage him. Fine. But at least my students are mature. That's good. That's here. So this is 1 over x plus I times x minus I. So Penrose mentions this is one of the fundamental mysteries of real calculus. Why on earth does this function? I mean, so here's a little bit of series for you. Remember this? 1 over 1 plus x squared, right? Is 1 over 1 minus x squared. 1 over minus, words, minus a minus x squared, right? So by the geometric series result, this is the sum, n equals 0 to infinity, of minus x squared to the n, right? Which you could write as the sum, n equals 0 to infinity, minus 1 to the n, x to the 2n. So that is the power series representation of this. For what x? For which x does the purple equation actually make sense? What condition is needed to go from here? Well, the condition that's needed is that the modulus, well, excuse me, the absolute value of the radius has to be less than 1. That's the geometric series convergence condition, right? So in other words, we need minus 1 less than x less than 1 if you sort through it. But this function, look at this function, 1 over 1 plus x squared, what's the graph of that? It's 1 at 0, right? And it limits to infinity both ways, right? It's just a kind of a tent of sorts. I mean, why should the power series stop matching that function? You know, why do you only get this, well, let's see here. Why do you only get this much of the function represented by the power series? Why does the power series stop representing the function 1 over 1 plus x squared? There's no trouble in the graph. The thing's smooth out to infinity both ways. Why on earth does the power series only work from minus 1 to 1 there? So Roger Penrose, in his book Road to Reality, lists this as one of the fundamental confusions or mysteries of real calculus, right? That mystery is resolved when we take a complex viewpoint. Because from the complex viewpoint, 1 over 1 plus x squared is 1 over x plus I times x minus I. And we have a clear understanding of where that blows up. Where does that blow up? What are the singular points here? Right, plus or minus I. So this theorem that I wrote down for you, in order to understand it, we have to take a complex perspective. So if we write down the solution to a differential equation using series methods, we can be confident that our series solution will exist on a disk in the complex plane, which is up to the nearest singularity. All right? But you got to keep in mind these kind of complex singularities. They don't just come in the real variety. Let me give you a specific example to try to, bring this to life a little bit more. If I was solving y prime prime, and let's work with the one I just worked with, x squared plus 1 y prime. And here, I'll put another one here just for kicks. How about x squared plus 4x plus 5 y equals to, we'll look at the homogeneous problem. So what are the singular points for this differential equation? Yeah, exactly. X equals plus or minus I are the singular points from this. This one, that's x plus 2 quantity squared plus 1 equal to 0. So this gives me x equals to minus 2 plus or minus I, right? These 4 points are my singular points. So to understand possible domains for solutions, I draw a complex plane, right? And I plot these trouble points. So like there's one here, yeah. There's one here. So here's minus I, here's I, minus 2. So there's one over here, and there's one over there. They always come in conjugate pairs for these real differential equations. Okay, so then you guys can give me any point along the real axis where we can expand a power series solution based on a real center point. Like, I don't know. Suppose I center the solution at the origin, right? So if I take z naught, for z naught equals to 0, you look and you go, aha. In the complex plane, if I look at the unit disk, right? That's the biggest disk I can get before I start hitting singular points. That means if I try to solve this differential equation centered at the origin with a power series, my solution is only going to exist and be a solution between minus 1 and 1. For essentially the same reasons that the power series, the geometric series representation of 1 over 1 plus x squared only worked there. So this would be my solution domain. So you guys pick another real number to look at solutions for. What do you guys want? Must I make all the decisions in here? 4. All right, I'll take that. Thank you. So let's suppose we put, and I guess I should put x naught, right? So here x naught equal to 4. And then as you look at in the complex plane, what's the nearest singularity that hits? Right? I was trying to do a circle. I didn't do badly, but the point is it hits the plus and minus I. It hits both of those on a circle of a certain radius. Oh, and you can see the radius right here, right? What's this radius equal to? Look at the triangle here, right? Right. So the height of the triangle is 1. What's this distance? So we got 4 squared plus 1 squared. So that's the square root of 17. And so for this, we would get an interval of convergence. Let's say the solution for 4 minus the square root of 17 to 4 plus the square root of 17. That's the real values which the solution would convert. Yes, sir. I meant, sir. Sorry. My apologies.
Why do you pick that to be 1 squared?
Because that's the distance. This is a 1, and this is a 4. The height, if I go I upwards, that's a distance of 1 vertically. Yeah. Adding I to a complex value is vertically translating 1 unit. Is a better way to say it. Yeah. Now there are trickier points, right? Like what if I put my center point here? Well, then it's not quite clear, depending on how you look at my picture. The question is whether that purple dot is closer to the plus or minus 2i, or is it closer to the plus or minus I, right? So, and of course we could pick the center point, because I'll do that because it's going to make my math easier. If we put, let's see here. the center point to be, where would that be? -1, right? Then I think that one actually hits all 4 singular points. Oh, maybe not. I can't do. My picture is just not quite. I believe that the distance, this distance, and that distance, and that distance, and that distance happen to all be equal. But the point is, the larger point is, you got to find the closest singularity that gives you a disk in the complex plane where the solution exists. We don't care about the complex solution. We're just interested in the intersection of that disk with the real axis that gives us the domain for the solution. So like this one, what's the length of these purple lines? Look at a little triangle, right? We're going from -1 to -2, so this says distance 1. This has distance 1, so this is actually square root of 2. So if we centered at x dot equal to -1, we would get -1 minus the square root of 2 to -1 plus the square root of 2 as the domain for solution. Now, what I'm telling you is a slight lie. This is the open interval of convergence. It may or may not be that one of the endpoints is actually included, right? Further analysis would be needed to decide whether or not the endpoints are included. You remember this discussion from calculus 2, right? It's just this is why we call it radius of convergence, because it actually concerns a disk in the complex plane. So it's an honest to goodness radius, really, that we're talking about. You should start to be annoyed that complex was not part of your curriculum, right? You notice how it actually gives insight to everything we're doing? Much like linear algebra. It should really be a core subject. But oh well. I am not king. Let's see here. Now, so does this actually solve problems? No, I'm just talking about the introductory. This is basically the guardrails, right? This shows us what to expect when we solve things. To actually solve things, we have to propose a solution and plug it in. Let's try one. What if I was going to try to solve, say, y prime prime minus y equals to 0? Oh, maybe let's make that an x. All right, I'm going to forge ahead. I may regret this. Y is the sum, n equals 0 to infinity of, let's say, Cn x to the n. So y prime is the sum, n equals 0 to infinity of n Cn x to the n minus 1, which of course we could drop the n equals 0, right? And just say n equals 1. Why is that? Because n equals 0 is just the constant, which is 0. Y prime prime is what? Similar calculation, n equals 2 to infinity of n times n minus 1, Cn x to the n minus 2. And so the overarching logic here is the same that we've been employing pretty much the whole semester, which is to guess a solution and then plug it back into the differential equation and, you know, twist the knobs, the adjusting knobs on our solution until we fit it, right? The difference up till now is we had undetermined coefficients, right? We had what? 1, 2, 3, 4 undetermined coefficients maybe, right? Or we knew that in our solution there will be a few undetermined coefficients because that's just the theory, right? Nth order problem has n undetermined coefficients in the ultimate solution and parameters in the solution to adjust for different initial conditions. Here, the starting point is infinitely many constants. C0, C1, C2, C3, C4, C5, C6, C7, right? So we have to somehow come to terms with how all of those have to be adjusted in concert to solve the differential equation. But the way to do that